So the next thing I want to talk about is the improvements to the color handling of HDMI 1.3. This breaks up into two basic areas. One is the deep color capability that I already discussed briefly. I'll go into a little bit more detail on that. And the other is improved colorimetry, or the adoption of the XVYCC standard. A very common way of describing the color that can be rendered, or colors in general, is on a diagram called a CIE, chromaticity diagram. This diagram, this horseshoe, basically includes all of the colors that can be viewed by a human's eye. The TV sets actually don't render the whole set. A typical TV set will render a significant subset of that. The standard definition television set specification included a specific red, green, and blue that were the maximum red, green, and blue that could be rendered by that. With HDTV, they improved that a little bit. They expanded that triangle out a little bit. But for the most part, it's still constrained within a significant subset. A good set of colors there. There's nobody's complaining about significant color problems on television sets, but nonetheless, obviously the display technology has improved significantly since the original standard definition and even HDTV standards were established, to the point that now display technologies can render colors outside of that range. And also the camcorder technologies have improved to be able to capture colors outside there. And in addition, game machines and PCs, which are actually creating the content, they have their own virtual world inside that they're creating the content. They create the colors, so they actually can create colors outside of this range. For all those reasons, we want to accommodate the broader color spaces that those devices or those advances can take advantage of. So HDMI has adopted an IEC standard called XVYCC, which allows the descriptions of color outside of this triangle. Previously, the HDTV standards were restricted strictly to that triangle, RGB triangle. But with XVYCC, now you can effectively represent any color in this whole range, well beyond actually the human visible horseshoe that's shown there. The issue with this, so that's great, we can now carry any of these colors, but the problem with this is now you have colors that can be way outside of the actual color rendering capability of a display. So for instance, if you have a display that's maybe better than the HDTV, maybe it's out here, but it's still not way out there. But if you have source content that has all of this color capturing capability, then the display needs to render all those colors somehow. And if it just, for instance, clipped them all to the closest color that it could possibly render, then all of these colors outside there would basically clip to the same color. And that would mean that any texture or pattern that uses those colors would all basically flatten. You wouldn't see any of that detail, you wouldn't see any of that texture. So instead of just clipping to one, the displays will instead typically map that onto a compressed part here, so you'll basically see some non-linear behavior there. So that compression from the source gamut, which includes all of the colors that might possibly be in the source, to the actual displays gamut, even if it's an enhanced displays gamut, there's going to be some gamut mapping. That compression or mapping of the source gamut onto the display gamut is something we now have to pay a lot of attention to, because now that we've adopted the XVYCC standard that can have a significantly broader expansion of color, then we have to pay attention to how those colors, those new super colors, are rendered on a display. The best way to make this work well is to tell the display what the actual gamut of the signal is. Prior to XVYCC, all of the signals were limited to here, and effectively the displays were limited to there as well. Now we've expanded the available source gamut, which means the displays need to know if the gamut truly goes all the way out there. The TV would want to know that, so it knows how best to map those colors that are beyond the standard triangle. In addition to the enhanced colorimetry, the XVYCC, we've added the more bits per pixel that I talked about before. We used to have 24 bits per pixel, which in a typical mechanism is broken down into 8 bits for blue, 8 bits for red, and 8 bits for green. So each of those 3 components has 8 bits. This 8 bits basically means there's only 256 pure blue colors that can be rendered. If you're looking at a scene of video that was captured from a film like a movie film, then that scene of may have a light blue sky pattern which goes from a very light blue to a very, very light blue. And only having 256 blues will cause that in the original film was a nice smooth gradation of blue to break up into a series of bands. So you're going to, instead of having a smooth, you're going to have a series of bands of blue. So that's going to be visible with the 24 bits of pixel data that we had in HDMI 1.2. With HDMI 1.3, that 24 bits has now gone to 30, 36, and even as much as 48 bits. We expect the 48 bits to be used mostly just in professional or industrial applications, but 36 bits is looking to be very common. So that 36 bits per pixel basically means instead of 8 bits for blue, we now have 12 bits for blue. Instead of 256 values of blue that we could have, we now have 2,000. So that gives us significantly more steps that can be rendered in that light blue to light blue sequence. So for the color improvements on HDMI, we've improved not only the range of colors that can be improved, but also basically the number of steps within that range that can be rendered.